Welcome everyone to this session. Good evening. My name is Kalyan. I am with my colleague Ashwini, and we'll be talking about our journey towards unified observability at Intuit using open source. And this was done at scale, and the challenge. We will talk about the challenges we faced, how we overcame those. In some cases, we had to contribute back to open source, improve open source. We'll talk about all of that. I used to be at Intuit till very recently. Now I'm the India head for SAI Group. It's a Symphony AI group. It's one of the largest AI, enterprise AI vendors. And so there are a number of companies that are part of it, such as Symphony AI, JazzX, which are more towards agentic AI, autonomous AI, AGI, and then there are some agentic healthcare companies such as GetWell, RhythmX, and Concert. And earlier I was at Intuit for about 2 years, where I was heading the platform team. I was the India site head for the platform, which comprised of Kubernetes, observability, and various other things such as API gateway, service mesh, messaging, and so on. And AI was again a key part of it with AI assist and done for you experience that was built into the product using agents. So I was working on that, and observability was a key part of it, which was completely owned by the India team. And there, for the 2-year period I was there, we took a journey to modernize AI, make it unified, bring up the level of abstraction. And the effort was led by Ashwini, who's the principal architect who was leading the effort. Ashwini.
My name is Ashwini. I've been with Intuit for about 9 years, mostly doing observability. I have been through various transformations that we went through, starting as a monitoring platform and all the way to the latest observability journey. I think today we are going to talk about the experience, the new experience that we tried building. In fact, we are still in the process. I would say that we are there at milestone 2, maybe, but there is some ways to go. We will talk about how we started, where we are today, and where we aspire to be possibly in around a couple of years.
Okay, thanks. So I'll briefly talk about the stack, and as I said, I was joined Intuit about 2 years back, and one of the things I was responsible for was observability. And when we looked at where it stood, first of all, the scale was huge, right? There were 300 plus clusters, 50,000 plus nodes. And then when we looked at the pillars, it was fairly siloed, right? So unlike most of Intuit, which had a platform approach driven largely by open source, I think this was led more by the operations team, and it was essentially proprietary vendors, and they were all siloed, right? So there was logs in one place, metrics were in a hosted solution somewhere else, and so they were all fairly disjoint, 3 different experiences, 3 different interfaces for the pillars, and the levels of abstractions that we needed to be able to do AI ops, to be able to have a really good unified experience where you could navigate across the pillars was missing. And so that was something we took up, and we also decided that we will be using open source extensively, which is done in any case across Intuit. I think that's the belief. So we thought we'll take that up as well. So as I said, I think there was, it was essentially a mishmash of various things. They worked well, they worked at scale. And so this was, the other challenge was also that we have something like 12 to 14,000 developers using all these systems. We are looking at petabytes of logs generated per day. We are talking about billions of transactions every few seconds, and some 10 plus billion transactions on the platform by multiple products. And so how do you change the engine of a moving car, right? Or a moving plane, essentially, right? So that was the challenge. And so we had to take an incremental approach that actually worked. And we also realized that if we use open source with all of the latest technologies and modern stack, you could see a significant cost savings, right? We are looking at something like 70 to 80% of cost savings at an Intuit scale. So that's tens of millions of dollars, right? So that's a huge saving, and much better user experience, and a lot of other metrics, right? Such as the key metrics we measure are MTTD, mean time to detect, and mean time to recover or resolve. And those were key metrics. And one measure of our success, one is the cost, the other is how do these metrics improve, right? And so and so it has to be data driven, and so that's something we did. Yeah, and so there's quite a bit of proprietary vendors and lock-in, and we wanted to avoid all of that. So I've talked about this. So and I should also mention that as a result of this, I think there's been a significant improvement in each of these metrics. I think MTTD came down from 23 minutes to 8 minutes, and MTTR was over 100 minutes, and it's down to about 30 minutes or so, right? So it's been a significant improvement, and it's a journey, right? We expect to see a lot more with the AI ops and agentic AI coming in. And that was the other thing, right? The cost was a key factor, and we also wanted to take an AI first approach. But then to be able to do AI, you needed actually all the pillars to be stitched together, the data to be correlated. You need a lot of metadata to describe all of that, and that's what the AI feeds on, and it can provide a lot of value. So these are some of the goals. Again, the idea was to keep the cost low. The most important thing is if there's an incident, how do I detect and recover from the incident at the earliest, right? That was the goal. And then also move up the level of abstraction. Since we had 3 different experiences and 3 different products for logs, metrics, and traces. So quite often the tendency is for people to look at logs, right? Whereas in the observability world, I think it's generally agreed that traces are at the center of it. But traces were rarely used because there was no way to navigate from one to the other. And so you were looking at, teams were looking at either metrics or logs or traces. And the idea is that can we move up the level of abstractions, right? One at a time. Maybe starting with an incident view, right? If I'm looking at an incident, or if I'm trying to investigate a particular interaction or a workflow, so that should be my starting point. And then ideally, the unified platform should give me all the observability data related to that incident, right? It could be logs, metrics, traces, profiles in the future, all stitched together. And that should make troubleshooting a lot easier and much faster. That's the goal. That's one level of abstraction. Moving up further, can we then build AI ops on it, done for you experiences on it? And that's something we're working on. We'll talk about it towards the end. Yeah. And again, by unified, it's important to have a dashboard where you can navigate from logs to metrics to traces, and with OpenTelemetry and exemplars, that becomes easier. But the goal is not to have a dashboards or many dashboards with hundreds and thousands of panels, right? Because it should be more incident driven. It should be more of troubleshooting. So ideally, you don't expect people to be staring at the dashboards, but it should be much more proactive, where you actually have alerts coming in with a lot of intelligence associated with that, a lot of insights with that. This is an issue. We think this issue could be caused by some of these things. Why didn't you look at those things, right? Then if you want to deep dive, maybe you come to the dashboard and look at that. But so just wanted to emphasize that unified should not mean just a single pane view, right? It's much more than that. Yeah, and as I mentioned, right, it should talk about what's wrong, right, and what you should do, or at least probabilistically what are some of the areas you should look at, right? What is ruled out and what is a possible cause of the error, right? And then with this goal, how do we work backwards? How do we define what should be my storage, what should be my query layer, and how do I process it, how do I ingest it, and then how do I apply AI to it, right? So, okay. And again, there are some concerns about, some of it is, I think, just the inertia. How do you overcome the inertia and get people to use this a different level of abstraction, right? Because people are, let's say, used to Splunk, then it's very difficult to get them off it. So that was, again, there's quite a bit of training. There's quite a bit of evangelizing that needs to be done. And then also make sure that the access to data is democratized. Then, it becomes much more easier for teams to be empowered and much more thing. So coming to this, right? So what are we then looking to build, right? So we are essentially looking at first of all fully transparent and unified collection processing. You don't want multiple ways of ingesting data, right? So ideally, OpenTelemetry has been the standard. It's extremely popular, very powerful. So why not start with that, right? And then the other advantage is that if all of the observability data is flowing through OTel, then I can, we have the receivers built in, doing that at scale. And in fact, some of the receivers, we have tried to scale it up and contribute it back. And then there is a processor, right, where actually I can add additional metadata. I can correlate some of these data. I can do various things, right? I can optimize, for example, I can drop some metrics which are unused or drop some logs which are unused. I can do some aggregation, do some summarization, things like that, right? So there's quite a bit that can be done at the processing level. And so OTel is, again, a standard powerful medium. So that's something that we are using extensively. And then work with vendor tooling as needed. And again, the abstraction as well, right? So one of the key things that we see is that when you look at data, there is the whole concept of data gravity, right? So this whole belief that let me get all of my observability data into one place, one centralized place, doesn't work, right? It's when you're talking about petabytes of data, billions of transactions every few seconds, it just doesn't work. There are latency issues, and it's not scalable. So the idea is that instead of bringing all data to one place, let's work with data where it exists, right? And so what should be centralized is not the data, but the metadata, so that we know where, and a catalog, right? We know where the data exists, how to find it, and then we need to do a federated search. And then we need the kind of tooling and the querying in place that lets you do all of that. Leverage AI, I think that was a key goal for us. And then we wanted to build on the existing triaging. I mean, we had incident commanders, we had different teams coming into place. How do you mimic that in an AI, with an AI experience? And Intuit has been strong on this whole done-for-you experience, where essentially AI does everything end-to-end, and then there could be a human factor where they approve it, but the whole flow, what is done today by humans can be automated with much higher productivity improvement and the time factor. And again, we are very strong on open source, so since we were redoing it, the idea was that let's use open source and move up the level of abstraction, as I talked about. And again, Intuit has been very big on open source. Argo platform, Argo CD and workflow and events, they were all created in Intuit and donated to CNCF. We have, again, a streaming and analytics platform, Numa Proj. There are a number of projects in that. There's Admiral, which is tied to Istio. And then we've contributed extensively to a number of projects. And so when we look at open source, right, what's the thinking, right? We are essentially, the reason we look at open source and not commercial vendors is that our scale, complexity, and diversity and heterogeneity, I mean, it's so complex that typically most vendors don't suffice, right? And when we sign up with the vendors, you get all kinds of commitments, but quite often they don't meet your needs. Whereas our approach is that let's take the best of breed in open source. Out of the box, that will not work for you, right? But it will meet 90 to 95% of your needs. And then how do you address the rest? And so we identify the gaps and incrementally we fix that, and we contribute it back to the open source community. And we have done that extensively in Istio, in Kubernetes, in API gateways, in Kafka, Pulsar, and so on. And quite a bit in observability, as Ashwini will be talking about. And again, we look at projects which are, where there's a lot of activity, which is not tied to one vendor, but where there's actually a good diversity of committers and contributors, work with the latest standards, and the modern stacks, right? Look at Iceberg. The whole Arrow ecosystem is extremely powerful, LangGraph, Ring, Trino, etc. Right? So, and then there's also, particularly for the platform teams. Now, if it's a application team, I mean, they might need microservices, they might need micro front ends to essentially have a composable experience and what the developers can do. But when it comes to platforms, right, we are looking very much at performance, scalability, and latency and cost. So considering that, we have had a bias for C++ Rust-based systems. ClickHouse is a great example. It's C++ based, columnar, and a lot of these systems have things like they have much better caching. They have thread per core. There's a vectorized processing support. There are frameworks like C* framework in C++, which is very, very good at concurrence, scalable processing. And most of the C++ systems, whether it's ClickHouse or Red Panda, ScyllaDB, they all use it. And similarly with Rust, right? There's Data Fusion, which is based on the Arrow ecosystem, extremely powerful. And Arrow, again, is columnar. There is zero copy, and there is zero serialization cost. And the whole ecosystem is extremely powerful. DuckDB uses that. Data Fusion uses that. Envoy, again, is a great example. And in cases where you have Java-based systems like Flink or Spark, Velox can be an accelerator for the querying and other computationally intensive steps. So those were some of the, and as I said, we contribute back extensively, as Ashwini will talk about it. So, okay. Yeah, so as I said, I think the federated search is extremely important when it comes to query. We are looking at a SQL-based query layer, and we need to have a number of connectors. For example, if I'm talking to metrics, I need a different connector, right? Something like a Prometheus or a Mimir. For logging, it's different. For traces, it'll be different, and so on, right? And with profiles coming in, and so on. So we need a diversity based on tooling, based on the nature of kind of data. Again, we are cloud-based, so we are looking at cloud storage. And the tendency also has been more at an object storage, because it's stateless. The redundancy and replication and some of those are built in. And so scaling up and down with a stateless system becomes a lot easier than with a block or file-based system. So that's been, again, the preference. And again, you need a tiered storage for some very critical aggregated data. Can we have it in a much faster system, and then have some more in object storage, and older data can be archived in a cold storage. And so that's something that's very important. So I think I'm running a little late, so I'll quickly talk about the big picture, but Ashwini, who's been the principal architect, he'll cover the details of each of these. But the idea was very simple. We have a number of sources. We ingest data at scale very efficiently, and then how do we store it, right? And then there are all these different pillars, and the idea is to have a unified layer sitting on top of it, and that's the level of abstraction we're talking about, and that's how observability experience is built in, and then you have the AI layer on top of it, which we'll talk about later. Ashwini.
Am I audible? Okay, thank you. So one point that I would like to add to what Kalyan added is when we talk about experience per se, what we realized is that the old system of having to look at UI and forcing the developers to look at multiple dashboards, multiple charts, and being able to infer or discern like what is going on, where it is going wrong, is not scalable anymore. Over the period of time that I have been at Intuit, we grew from over 2,000 plus services to about 8,000 plus services now. And this number is going to explode again, given that we are making a big push towards agentic experiences and so on and so forth. And there is a lot of nano architectures, nano services, microservices that we have been seeing. And so the amount of telemetry data has just simply exploded. So this notion of forcing a user to look at data is no longer scalable. It just won't work. So with that, and one other point that I would like to add is that given the recent developments that have happened both in the Gen AI space as well as in the agentic space, it becomes imperative that we can exploit a lot of that because observability itself is a data problem. And when you're building a system like this, you're essentially building a data product, right? So any data product these days without support for Gen AI or doesn't leverage the power of LLMs is probably not the right solution, or maybe needs a little bit of help. So that's one of the primary motivator towards focusing heavily on the query layer. And picking SQL as a dialect, because in our experiments and also some of the experience that we have seen so far, Gen AI seems to be doing pretty well with SQL, and it is able to generate the queries that work, like let's say 90+% of the time. So, and training is LLM to generate SQL has been pretty, I mean, in the sense, we had seen some reasonable success, especially when we look at RAG-based techniques. But there are definitely some outliers. So with that, what did we do? Like, obviously, we are AWS heavy. So we used S3 as a storage. And Parquet data format, especially most of the queries typically that you execute on an observability system involve aggregations. And what's better than a column format, right? Columnar format to run those aggregations. With Parquet especially, we can obviously take advantages of projection push down, partition push down, and potentially the compression ratios that I have seen at least is about 140x with the kind of data that we have been ingesting into our store. So, which makes Parquet a good choice or good fit, in my opinion. And we picked Iceberg table format. Primarily, I mean, there is most importantly, the driver is around the data profile. What we have seen increasingly happen is that we are not able to basically test for all the combinations in pre-production. So most of the time, the data shape or the data profile, we end up discovering in production. And we have to go back to pre-prod, try to mimic that error or whatever the scenario that we are testing for. And so there is a lot of room, we felt that there is a lot of room, and we need to build in that flexibility so that our schema can evolve, partitioning can evolve, and which makes Iceberg a good fit for building systems like this. And of course, Iceberg also brings in, and in fact, it is continuously evolving. And I'm excited about the latest version 4 that they are going to, that is still in the works. But I mean, that's a work in progress. Trino as a query engine, obviously, we laid down that we need some federated query layer. And with the amount of number of connectors that Trino has, one of the requirements that we have is like, this new system is in place, but then there are all these existing vendor solutions that we cannot simply throw away on day one. So we need something that can work with the existing solutions as well as the new system. And that made Trino a choice for query engine. ClickHouse we used as a faster analytics store. Most of the time debugging at scale, especially when you have too many components, too many stacks involved, the focus is not so much on finding the problem, but the focus is more on eliminating the necessary components, right? So we defined what we know as golden signals. I mean, we call as golden signals for each of the stack. And we store these golden signals in a faster analytics store. The idea is to quickly look at these golden signals and eliminate the suspects and reduce the list of possible suspects so that we can start diving deeper into the signals emitted by those stacks, right? So that's where ClickHouse comes into picture. Minimal API, we thought about building, we had a debate about this, whether to build an API around this data query layer or should we just expose the SQL as is. Given that we are moving towards a much more done-for-you experience, done-for-you experience at Intuit basically means that you have, you can imagine an agent actually doing the work of, let's say, incident commanders, incident engineers, incident responders, etc., finding out and digging more and more pieces of information that are connected to the incident and presenting a summary of what has gone wrong and what are the possible recommended actions, right? So that's the experience we're shooting for. So to build such a system, introducing an API layer seemed like redundant. And given our success, and this is like, we did some POCs, we did some experiments with generating the SQL queries using LLMs. And we have seen good success, and the success rate kept on improving as we tested more and more. And that's the reason we decided that we will minimize the API that we are going to build. So minimal API. Ingestion time metadata, this is critical because majority of the time is spent in identifying the attributes of the failures. In the sense, when I say attributes of the failures, what are the dimensions that you need to search for to formulate your query so that you can go and search in logs, traces, or metrics, or any of the events, right? The key is in identifying that set of tag value or key attribute key value pairs, which will tell you the story of what is the failure profile looking like. And this cannot be solved once your data is in the store, right? You have to generate, at least have some basic analytics while the data is still in flight, while it is still getting ingested into the store. And that is where ingestion time metadata comes into picture. We maintain a very basic analytic counts for each tag value. What are the error counts that we have seen in this particular time window, so that we can pass them as hints to the query engine or to the LLM agent actually to identify the set of tags that it can use to start the investigation, right? And then as it discovers more and more, it can refine the queries, add more tags or delete some of the tags, and be able to summarize the failure. Summarizing the failure typically helps engineers save a lot of time. Otherwise, we have seen situations where people have to score around like multiple systems. Given the multitude of tools that we used to have. So that was a time saver. In-stream querying. So this basically, the idea came from while we were trying to solve for the dashboards and alerts. So we had a lot of dashboards and alerts that were created on vendor tools. And some of these dashboards, because at that time, and even now to a large extent, the investigation proceeds by looking at dashboards and alerts. And if you wait for actually the data to get stored and then query, it's susceptible to multiple things. One is there is a lot of cardinality explosion that we have seen happening recently. And in fact, this cardinality is increasing day over day. So it's not easy to just store and query anymore. It's also susceptible to ingestion delays. So what we thought of is, better than storing and querying the data, how can we run the queries while the data is in flight? We can avoid cardinality, we can avoid delays due to ingestion. And so we explored Arrow and data fusion. We have had some success. And of course, we are also evaluating DuckDB as an alternative, because at least I think that DuckDB is less complex to maintain, probably, over an Arrow plus data fusion system. This is a schematic of how an in-stream querying will work. You can imagine a process space. Data points are coming in, converted it into an Arrow schema. So again, if this setup works only with predefined queries, which means that you already know what queries you are executing for. Basically, this is to cater to existing query mechanisms or the basic triaging that developers typically have in place to detect like these signals, right? That something is going wrong, not necessarily dynamic or runtime in nature. I think Apache Data Fusion and DuckDB both are choices here, and we'll probably converge on one or the other sooner. Again, alerting at source, like Kalyan alluded, we don't want to spend time moving the data around to a central place and then run this process the data for any kind of signals or so on and so forth. So it's always better to alert at source. So we have 300 plus clusters. Each cluster hosts a number of services. So why can't we run the alerts at a service level in cluster itself? And second thing, threshold-based alerting is no longer feasible at the scale that we are operating. We are about close to 5 million PPS at this point, in terms of just the time series. So we decided on using anomaly-based detection. So anomaly-based detection, one limitation that we ran into was which stream processing system should we use? Should we develop something from scratch? And ultimately, we ended up doing just that. So we have this project called NumaFlow, which is a part of the NumaProj open source project. It's an open source stream processing platform. It's not trying to be Flink or Spark or anything of that sort. It's a very simple Kubernetes native stream processing platform. It can support heterogeneous tech stacks, and it definitely is ideal for simple map and reduce operations. No joins, no broadcasts or anything like that you get in Flink. The key motivation was to support Python models, while the data crunching may happen using Rust or C++ or something, which is far more efficient than Python. So transitioning to the new solution, how do we transition them? Newer experiences, they evolve side by side the existing ones, which means we don't just simply throw away the existing stuff. We have to build this experience and slowly transition the developers away. We don't want to force developers to adopt this new solution. I mean, it has to be a lot more smoother and zero effort, which means all your dashboards, alerts are also available on this new system. And plus, you have this experience which will tell you what is wrong and what you could do to get out of the situation, which most likely should encourage developers. And in fact, we have seen some good reviews from the initial versions that we have put out there. Phased approach, I mean, I think it's pretty well understood. So specifically, getting into pillars. Logs, we have seen logs growing at the rate of 50% year over year. Again, it goes back to the fact that we have been refactoring quite a bit. So there are a lot of nano services and microservices. Huge search volume, of course, dashboards and alerts. Legacy and a mix of structured and unstructured data, which means whatever solution that we are talking about, it has a columnar data format and query engines, etc. It works perfectly well for structured data, but not so much for the unstructured data. For unstructured data, we still have to rely on some vendor tooling, which happens to be Splunk at the moment. So we need to have this solution working side by side with Splunk. And you have Trino as a federated query layer, which will essentially can query the data from different, any of the systems, wherever the data is stored in. That's the idea. I'll skip this slide. Logs. So when you have Splunk, they also have Splunk Forwarder, which is the collector to tail the log files where it gets the data from. The first thing that we did is, okay, let's completely own the collection, which means we will have FluentD, FluentBit as a collector. And the first hop from the node will be an S3. And from S3, you can have various pipelines, one pipeline to deliver to Splunk, one pipeline to ingest the data into Iceberg tables. And on top of it, you have a Trino as a query layer. And again, to solve for dashboards and alerts, we use GenAI plus RAG-based approach to basically train translation of queries from Splunk query language to SQL. And it worked well. I mean, in the sense, we didn't get 100% success, but we almost got to a point where the number of manual changes that we had to make to dashboard queries, etc., were minimal, manageable, I would say. So this is a schematic. So you have log shipper, which is FluentD, gets into a bucket. You have SQS notifications, Spark picks it up, ingests the data into Iceberg, gets queried by Trino. So what are the challenges that we saw with this? One, definitely, turns out there is a lot of legacy at Intuit, which means that a lot of the systems were using logs as a primary monitoring mechanism because most of the applications are at least 2 decades, if not 3 decades old. So the observability as a concept didn't exist back then. So logs was a primary thing, which means that there was a lot of aggressive end-to-end latency demands, which means from the time the data is produced, I want the data to be available like within 30 seconds or 60 seconds was a requirement. And of course, wide query windows. I mean, because they were not sure whether the data will arrive in time, they will go back and say, okay, I want to scan the last 5-minute data or 10-minute data or 15-minute data, right? Which means that a lot of queries are overlapping. And if we try to solve for the end-to-end latency, we will end up with too many small files, which basically mean that too many snapshots in Iceberg, which means that the size of the manifest file will be huge. And whenever Trino tries to process this manifest file, tries to understand what's going on in the snapshots, it will just run into out-of-memory issues, right? So we tried testing with Bloom filters, which means initially we looked at the queries that are being executed, and then we tried to formulate the partitioning scheme based on the queries, etc. But that didn't help. And in fact, old queries were never a good predictor of what the future is going to be. So we went back and said, okay, we are going to use only time-based partitioning. And for all alphanumeric columns in the data, we are going to use Bloom filters. And we put in place compaction and expiration of snapshots to keep the things under control, which means manifest files become manageable by Trino. And this solution, and I'm talking about unit cost, it worked out to be 40% cheaper than what we are paying already. Right? Metrics, pretty much the same story. Growth is phenomenal, 60% in the last 2 years. And metrics, one of the things was a lot of the data that was collected was going unused because a lot of the attributes had very sparse data. So we went with in-cluster Mimir, which means we will not host any central Mimir, but we will deploy Mimir in each Kubernetes cluster, in-cluster, and we will process alerting any kind of pruning, removing unused metrics, etc., right then and there in the cluster, which also helps with reducing blast radius and so on. Yeah, so Mimir architecture, this is a deployment topology of Mimir, I would say. I mean, I'm not talking about the UI or in almost all of these cases, we used Grafana as a dashboarding tool, but I'm not talking about it because we wanted to steer developers away from that. So while Grafana is still in place, we are building this system which will allow you to,
we have 3 minutes.
Yeah, sure.
Sorry,
yeah, traces and events. I think I'll just take 30 seconds.
Yeah.
So the key part is everything is the same. Traces are structured data. One thing that we started seeing is the amount of data contained in a trace was become unmanageable. So we had to introduce LLM for trace summarization, which worked out well in the sense now people no longer have to look at the trace view or a Grafana plugin, etc. They get, the system tells them this is what has happened in this trace and this is where the bottlenecks are. Sorry.
Yeah, thanks, Ashwini. So, sorry, we ran a little long. So, you have the thing? So the slides are shared, so please, you could go through that. But yeah, metrics and traces, we had something similar. So I'll briefly talk, we just have a couple of minutes left, so I'll talk about the next steps, things we are working on, or that the team is working on, rather. So one is, as I said, having a done-for-you experience, how to use agents to do incident recovery. I'll talk briefly about that. Profiling is one pillar that's missing. Now there's a very good profiling support, particularly with eBPF. So we are actually looking at that. And then there's still some gaps. I mean, the support for symbolization for Java, etc., is still a little weak. But as it gets mainstream, we'll have profiling. And with the exemplar support, it's very easy to move from traces to profiles or metrics to profiles. That's something we are looking to do. Similarly, we were using Igloo, but Unity catalog is very impressive. So that's something we are looking to do. It's elegant and powerful with, with all the different multi-layered architecture. I'll not go too much in the interest of time, but there's a lot of governance and security and model support and everything else that's built into Unity. So it's a value addition for us. And then we are also looking at AI observability. I'll just briefly talk for 30 seconds. So the incident recovery agent, again, the idea is that how do I automate the complete flow, right? And here we try to mimic what we are actually doing, what the teams are doing today, right? With incident commanders and so on. So at the heart of it is an incident agent. What does it look at, right? So one key thing is an RC database. So we have all of the incidents in a vector database, and then based on the context and the current incident or the current alerts that I'm having, I can do a vector search on the RC database. Knowledge graph is extremely important again. We use a mix of dependency graph with overlay of red metrics, lot of context, and lot of infrastructure related information. And then combine the two, the LLM can become very powerful. And then there are lots of other tools and services that we use, whether it's logs, metrics, traces, change events, and then the platform teams and other teams have various components. So, for example, I can talk to my Kubernetes layer, ask, is there an issue here, right? Or an API gateway. So those are some of the things that we are using. And briefly, some learnings, right? Knowledge graphs are extremely powerful. And one of the lessons we've learned is that everybody's talking about AI, Gen AI, and agents, but LLMs are, and this is again based on the observability we have done, LLMs are an order of magnitude, more expensive, right? And in terms of compute and everything, compared to a knowledge graph or a vector search. Similarly, an agent is much more computation intensive. So, not to use them when not needed, right? So, for example, if I'm doing some generative AI, if I'm doing some React, right, reason, and act, there I probably need it. But in many cases, I don't need agents. I can, if it's a semantic routing and some lookup, I can actually do it in knowledge graph or vector search. Similarly, if my path is very deterministic, I know exactly what needs to be done, I probably don't need an agent. If I have a multitude of choices and based on context and information, the agent needs to figure out what needs to be done. Only in those cases, agent is needed. So we've resisted the temptation to avoid using agents everywhere, using LLMs everywhere, and that's made a much better systems. And it's still not mature, so we often need human in the loop. So idea is that agent tells you the summary, this is the problem, these are the red flags, these are some of the diagnostic messages, this is the probabilistic root cause, what do you want to do, right? So, that's something that, and explainability is important, and with the tools that we have, I think that's pretty much possible today. And again, the AI observability, Gen AI brings in another dimension, particularly with agents and everything, and particularly with an agentic framework where you have hierarchy of agents talking to LLMs and tools. You really need to know what's the bottleneck, right? And some of the findings I'm talking about came from having AI observability, again, in the interest of time. So we've looked at two open source, LangFuse. It's extremely powerful, but it's not completely tied to OTel. So that was one challenge we had. But I think with the latest LangFuse, I think that's being addressed there. I think much closely integrated with OTel. OpenLLMetry is much better in that sense. It seamlessly plugs into our OTel network, and then any data sync you have or any persistent store we have, you can actually use OpenLLMetry. So those were the two. So we started with LangFuse, and I think the intent is to move towards OpenLLMetry. And again, there's a convergence happening. So initially, many tools started with more of a tracing because that's key to monitoring your agents. But then you also need evaluation, metrics, and so on. So for example, LangFuse is integrated with Raga's framework. And so now tools are giving you, everything under one roof. Again, thanks again. I'm sorry we went a little long. Any questions? Yeah.
So you've been talking about using. Sorry, I'll get the microphone. Thank you. So you've been talking about using agents to kind of do some incident commands, etc., and kind of start some of this off and try and find root cause analysis, etc., with the human being in the loop at the end of it. Have you found that there's been kind of like a degradation on people actually then looking and trying to dig deeper into signals when you've got edge cases which the LLM can't use, or is the LLM kind of finding most of the problems anyway, and it's narrow enough that you can then start to go and use the old dashboards or something like that to actually go and find what's actually going on?
Yeah, so maybe I'll go first, and then so what we have found is that even though we have a rich repository of RCA documents, etc., which should theoretically allow us to get somewhere to a place, a lot of these inferences that LLM comes back with depends on how good your RCA documents are. Unless and until your incident is on priority 1 or priority 2, people don't do an extremely good job at identifying what are the exact root cause and how it. So what is also important is what did the engineer actually try to diagnose, and what it didn't work, right? So that is how LLMs learn as to, I should not go down this path because this path ended in like a wall or something. So it's still, I would say it's still a journey. We have put in some things in place now. For example, if someone comes up with an RCA document, I would mandate that I run through an evaluation and actually see what can LLM give me a basic reasoning of like, what happened here, what is the decision tree that went into actually solving this incident. So without that, if I got your question correctly, without that we have seen that the output is a little mixed in the sense LLMs do tell you some probabilistic pointers, and sometimes it hallucinates quite a bit. It goes out to internet and tries to find something and then throws at you. And so we basically introduced user feedback as well. So whenever user says that, okay, this is probably wrong, this doesn't apply here, this is too generic, or those kind of feedback. So we expect the system to evolve and get better for a period of time.
Yeah, and one key thing is with LLM to work, right? You have to narrow the context, and that's where the knowledge graph, for example, comes in, right? We have golden signals, we have anomaly detection, so we can point to those anomalies in the knowledge graph with the overlay of red metrics and so on, right? I can say that this node is down, or here there's huge latency. So why don't you look at some of these edges and nodes in the graph, right? As opposed to looking at everything. So narrowing the context often helps. But still, it's still maturing. So there's a human element required.
Yeah, thank you for the talk. I enjoyed it. A couple of questions. One was like, you guys tried to solve the small file problem with compaction. Were you sort of still able to keep up with the volume, and what was like sort of the staleness on the data when you were done? Like, I get the cost reduction.
So the reason why small file problem actually started is because of the partitioning scheme. We looked at the existing queries and we said that, okay, hey, these are the fields on which people are querying. All the queries are written on. And so let's mirror our partitioning scheme to whatever the queries are asking for. Right? That was the quickest way to solve for that, right? But we found out that the entire thing is extremely brittle, that the moment I change slightly, ever so slightly, like an additional dimension comes into picture and starts becoming the hot dimension, this entire thing falls apart in the sense, the query timeouts and so on and so forth. So that's where that was the root of the small file problem. So no matter how much compaction you do, if your partitioning scheme is not right, small file problem doesn't go away, right? I mean, it can only merge against time. So we had to take a step back and say that, okay, we will not do these additional dimensions because in the future, whatever queries that are going to come to the system, let's not be informed by what people have been looking for over the past decade. So let's break from the past. We will tolerate some latency. We will definitely crunch some data which is unnecessary probably. We will pay some cost, but at least we will have the system. We have some flexibility built into the system. So we went back and said, okay, partitioning only on the time, and for anything else that is alphanumeric, we will use Bloom filters. So that really helped. So on top of it, if you apply compaction, then you end up with, you have to define, we put a file size of approximately 256 megs per Parquet file. So that means that we have finite set of files which were manageable by our Trino workers. So one other thing that I didn't talk about is also that Trino is good as of now, but Velox is also very compelling, like Project Gluten. So we plan to explore that.
So with all of those changes, what did your P95, let's say for like the last 1 hour of logs data, I think, look like?
About the end-to-end latency?
Not the end-to-end ingestion latency, but like query latency, because like as compaction is running as an asynchronous process, I'm assuming that users are also actively querying for this data.
In some cases, yes.
Okay.
But that's where the in-stream querying actually helps, because in-stream querying removes like a lot of this immediate, querying on the immediate data. And so a lot of the queries that will come onto Trino are exploratory kind, whereas all the scheduled queries and alerts that you are configuring, they come into the in-stream querying, which means the data is actually hot there, and that's one of the ways in which we minimize the amount of query. But you're right in that while the compaction is still happening, we did see latencies. So there is no way around it. I mean, we have to tolerate, like, we have to have a Trino cluster that is big enough to crunch all the small files, or you try to minimize the query workload.
Got it. And one last question, if I can. You mentioned something about like at streaming time, you're maintaining some counts, like error counts, like by certain dimensions. Like what was the user journey where you would use those counts? You mentioned something about how that would inform the search or focus it. Like what search are we talking about?
Sorry, I think we probably have to break. I think we can take this offline. We are already a little late. But thanks again. We enjoyed presenting. I hope you all had fun listening to us. Thank you.